Hi, I'm Martin Sweatman, and in this video I'm going to review a new paper that suggests the Younger Dryas cooling event nearly 13,000 years ago was triggered by a volcanic eruption, namely the Laacher See eruption in Europe, rather than a cosmic impact, as is often thought to be the case. Now, until now we've had over 100 scientific papers that all agree the Younger Dryas event was caused by Earth's collision with debris from a disintegrating comet, and only one paper that suggests it was caused by the Laacher See volcanic explosion. And I reviewed that paper a few months ago and pointed out its flaws. Now, this new paper by Sun et al. Appears in the journal Science Advances, and the key focus of their paper is on rare elements or platinum group elemental abundances, and especially the osmium isotope ratios found in the sediment of Hall's Cave in Texas. And here's a picture of the sediment from the cave, and you can see the change in the type of sediment indicated by the red dashed line here, which the authors take to represent the Younger Dryas boundary, which signifies the change in climate back to Ice Age conditions for over 1,000 years, nearly 13,000 years ago. Now, the first thing to say about this work is that it's certainly true that abundances or layers of rare platinum group elements found in sediments and ice cores are a good indicator of a cosmic impact or a volcanic explosion. And the question is, how can we tell the difference? Well, we know a lot about the composition of asteroids from the inner solar system because of all the meteorites that have been collected over the years. And we also know a great deal about the kinds of geochemical signals produced by volcanoes, because they happen all the time. But we don't know nearly as much about the elemental composition of comets, whose origin is in the outer solar system. And the Younger Dryas impact is proposed to have been caused by a comet, not an asteroid. So we should be cautious when assessing specific platinum group metal abundances and either confirming or dismissing a cometary origin on this basis alone. Now, in the case of the Younger Dryas impactor, it's thought to have been rich in platinum because of a strong platinum spike found in the GISP-2 Greenland ice core right at the onset of the Younger Dryas cooling. And here is that data again from the paper by Peteyev et al. In 2014. So sampling of the ice core here, so we've got the age along the bottom, and along up here we've got the platinum abundance, and here the iridium abundance, and on the bottom here we've got various sulfate and ammonium spikes in the ice core. Now, the sampling of the ice core here is about every 3 years roughly, so we have a very good correlation between this platinum signal, thought by many to indicate a comet impact, and this cooling, thought by many to be the Younger Dryas cooling, or the onset of the Younger Dryas period. But notice how there is no equivalent strong iridium spike in the ice core. There is a smaller spike, but it's not nearly as strong as the platinum spike. And this is confusing, to have platinum without similar changes in iridium if interpreted in terms of known types of asteroid, which adds support to the likely cometary origin of this impactor. It seems the platinum group metal composition of comets can be quite variable and not necessarily the same as the kinds of asteroids that we know about. But also note this sulfate spike here, around 100 years earlier than the platinum abundance. And because these are measured in the same ice core, the GISP-2 ice core, this offset of 100 years is correct, it's real. And we can see that according to this high resolution ice core, there is no cooling following that event. In fact, if anything, there is a warming trend. And we see the same pattern repeated in this paper by Klatechka et al. In 2018. And they analysed sediments from the bottom of an ancient lake in the Czech Republic and found that these microspherules here in the sediment core from this lake which they interpret to represent the Younger Dryas comet impact, post-date. Okay, we've got the depth here correlates to a timeline, so it post-dates by about 100 years this tephra layer here, which they interpret to be the Laacher See volcanic explosion. So the tephra here is essentially tiny particles of rock and dust, and it has been chemically identified as belonging to the Laacher See volcanic event. And again, when we compare these signals with this thorium potassium trace or signal, which is a proxy for rainfall and therefore climate, we see that if anything, the Laacher See event, signaled by the peak in the tephra here, correlates to a rise in rainfall and therefore temperature, and not a fall, while the impact spherules over here correlate to a fall in temperature. So it's clear from both the GISP2 ice core and this lake sediment core from the Czech Republic that the Laacher See event here had nothing to do with the onset of the Younger Dryas mini ice age. So back to the new paper under discussion by Sun et al. How can they have concluded that the Laacher See explosion caused the Younger Dryas climate change instead? Clearly they ignored this earlier evidence and based their conclusions only on what they found at Hall's Cave, and that's bad science to ignore earlier evidence. So let's look at what they found at Hall's Cave that convinced them they were right and almost everyone else is wrong. So here is their main evidence. It's essentially a plot of the abundances of osmium on this scale here, which is a platinum group metal, and over here we have the ratio of two osmium isotopes. Now conventionally it's thought that when there is a spike in osmium together with a dip in this osmium isotopic ratio, that this signals either a cosmic impact or a volcanic eruption. But remember what I said about interpreting specific elemental abundances. We have to be careful because not a lot is known about them for comets from the outer solar system. So what do they find? Well, first, before we even look carefully at this plot, we need to check the age depth model. Okay, we have the depth here and the age here, because it's obviously crucial. They assume that the Younger Dryas boundary, and therefore evidence for the cause of the Younger Dryas mini ice age, is signaled by a change in the color of the sediment at this position, which is 151 centimeters deep in the sediment. But how do we know this is correct? Looking at how they construct their age depth model in the supplementary material accompanying their paper, we see that it's constructed from just 6 radiocarbon measurements at these sediment depths. And the first thing that strikes me about this is that there are no error bars shown here. Now it's unlikely the error bars are smaller than the sizes of these symbols, because we know there is a lot of error in the radiocarbon calibration curve they used. So it seems to me they've neglected to plot the radiocarbon dating uncertainties or error bars. Well, that's just another indicator of the kind of science practiced by these authors. It's sloppy work. I wouldn't let undergraduates get away with this. So it's surprising to see this in a paper that has been peer-reviewed. In fact, the uncertainties or error bars are never mentioned once in this paper for the radiocarbon dating. Even in this table, where they tabulate all their measurements and had another opportunity to tell us about these radiocarbon uncertainties, they don't. They list the osmium measurement and its uncertainty, but not the radiocarbon dating uncertainty. At first glance then, we can have no confidence in this age depth model at all. So how can we know if they've correctly identified the Younger Dryas boundary? Well, fortunately, we have this abstract of a poster presented at the AGM of the Geophysical Union in 2009. And these authors of this poster make it clear that the impact proxies normally associated with the cosmic impact, thought to have occurred at this time, occur only within a thin band of sediment between 151 and 153 centimeters, precisely where the sediment changes color. Now, it's a shame this work was never published in a peer-reviewed journal, as it looks to be important, Nevertheless, on the basis of this poster abstract, which I would normally be very hesitant to use because it won't have been peer reviewed, it looks like the authors of our new paper, Sun et al., probably did correctly identify the Younger Dryas boundary. Okay, so back to the age depth model. And according to this plot, 100 years at the time, or at around the time of the onset of the Younger Dryas cooling, corresponds to just 3 centimeters of sediment. So in terms of the stratigraphy, the Laacher See volcanic explosion and the Younger Dryas comet impact are expected to be separated by just 3 centimeters in the Hall's Cave sediment. And these authors sample the sediment only every few centimeters. So this has to be regarded as a low resolution record of events. Certainly it's much lower than the GISP2 ice core, which has been sampled at intervals of about 3 years, and the lake sediment core from the Czech Republic, which, taking into account the mixing of sediments there, has a resolution of about 10 years. Now, here at Hall's Cave, the resolution is about 50 to 100 years. So again, we need to be careful in assessing the evidence from this cave. However, we can expect that if the Younger Dryas event is located at about 151 to 153 centimeters, as the impact proxies suggest, then the Laacher See event would be located at around 154 to 156 centimeters. All right, well, that was a lot of background, but it's needed to properly interpret the evidence from this cave. So let's now return to the main result of this paper, which, if you recall, is plotted here in terms of absolute osmium abundances and the isotopic ratio of osmium. Now, probably based on what we expect to see from these earlier papers, we should expect that the cosmic impact occurs here at around 151 centimeters, while the Laacher See eruption corresponds to this osmium anomaly a little lower down. So this sediment core looks to be in perfect agreement with these earlier papers, and yet the authors instead suggest that the osmium anomaly here is the Laacher See eruption. Now, why would they do that? All right, so we need to understand why the authors rule out a cosmic impact for this osmium anomaly here. What is their reasoning? Well, first we need to realize that at this depth, 151 centimeters, and only at this depth, they actually took 5 samples and not just 1. And the 5 samples correspond to these 5 symbols. And they're all taken from the same height in the sediment, all from between 151 and 152 centimeters. But we need to be careful here because it's clear from this photo that the boundary layer is not perfectly flat. It undulates slightly. So these samples, which are taken laterally or next to each other at 151 centimeters, are not all measuring exactly the same depth or exactly the same time in the sediment. There'll be small differences in time due to this undulation of the sediment. And remember that each centimeter of sediment here corresponds to about 30 years. And here we have a 2-meter scale. So we don't expect their samples to be identical, even though they are taken from exactly the same height or depth in the sediment. And in fact, that's exactly what we see. As you can see, these 5 different samples at 151 centimeters all have different osmium abundances and ratios. Now, the author's argument for rejecting a cosmic impact at this time, at this level, is that although there is an anomaly in the osmium abundance and ratio in one of the samples, this one, signifying a volcanic eruption or cosmic impact, there is no abundance in platinum at the same level. And remember, our comet is thought to have been rich in platinum. So that is what they're saying here. The unradiogenic samples with osmium ratios less than 0.42, including the one sample in this group at the Younger Dryas boundary layer, have low platinum group metal abundances that are also similar to upper continental crust. Hence there is no enrichment in these elements spanning across the Younger Dryas section in Hall's Cave. Therefore, they say, this rules out the comet impact scenario and rules in the Laacher See volcanic explosion scenario for the Younger Dryas climate change. However, they're being selective and a little bit dishonest. You see, they say there is no enrichment in platinum at this level, 151 centimeters in the sediment. But that's a little porcupine, isn't it? When we look at their tabulated data in the supplementary materials, what we actually find is a different story. You see, I've highlighted in yellow the 5 samples from 151 centimeters, which we expect indicate the Younger Dryas event, and below in pink are 2 samples from 155 centimeters, which we expect indicate the Laacher See event, but which the authors suggest is a different volcanic event. Now, don't worry about the dates here in this column. Although all 7 of these samples have the same radiocarbon date, they are later passed through a Bayesian statistical analysis which separates these 2 depths in terms of their dating by over 100 years. And it's that Bayesian result that they plotted for their age depth model. So now this table instead contains their raw measurements. And as you can see, if we look closely at these 5 samples at 151 centimeters, we can see that one of the samples has an osmium anomaly, the 5th one here, but no platinum anomaly. And another has a platinum anomaly, the 3rd one, but no osmium anomaly. So the authors are being selective in their interpretation of this data when they suggested there was no platinum anomaly at this level. There clearly is. It seems that whoever reviewed this paper didn't bother to look at the supplementary material here. Easily done if you're a busy academic. They should have picked this up. And then when we look at the lower sediment at 155 centimeters, where we expect to find the Laacher See event, we see there is an osmium anomaly, but no platinum anomaly. Although there are only 2 instead of 5 samples at that depth. So what should we make of that? What's going on here? Why are these samples from the same level giving very different results? Presumably it's because the boundary isn't perfectly level, as I explained, and so samples taken at the same level at different lateral points actually correspond to different dates. Or perhaps instead the platinum and osmium abundances are patchy. This is the so-called nugget effect. Essentially, this means that there are lumps of these rare metals probably bound up inside other kinds of particle. Or perhaps both explanations are correct. Perhaps the undulating nature of the boundary and the nugget effect are both in play here. Well, whatever, it's perfectly clear the authors have been selective. But we know, based on the accumulated evidence from over 100 other papers, that the Younger Dryas event was almost certainly caused by a comet impact. So it seems these authors are using a sleight of hand. They say the elemental abundance in Hall's Cave at the Younger Dryas boundary are incompatible with a cosmic impact origin. They aren't, especially as we know little about the elemental abundances of comets. In fact, we could equally argue they are incompatible with the volcanic origin, because only 1 out of 5 samples at that level has an osmium anomaly. Moreover, based on evidence from the GISP2 ice core and the Czech lake sediments, it's likely this osmium spike at 155 centimeters corresponds to the Laacher See volcanic event instead. So, as with all things in science, we need to ask, how much confidence can we have in their conclusion? I would say very little, because they have probably misidentified the Laacher See event, ignored the platinum abundance they found, ignored much higher resolution data from other locations, and because their discussion of elemental abundances relates to asteroids and not necessarily to comets. Oh, and there's one more thing before I finish. If we look again at their data from the sediment at Hall's Cave, we see that the highest platinum spike recorded across the whole 4,000 year sequence actually occurs here at a time very close to the end of the Younger Dryas mini ice age, and there is no accompanying osmium anomaly, although they only took 1 sample here. So does this mean the Younger Dryas mini ice age was both initiated and ended by a comet impact? There seems to be mounting evidence that the end of the Younger Dryas period was very unusual too. Well, if you enjoyed that, you can find out more about the Younger Dryas impact from my book and blog, as well as other videos on my channel here.